Hello and welcome to part 3 of lesson 1 in unit 7 exponential functions in our grade 11 University College math class. So we've looked at exponential growth. In this lesson we looked at a party where we saw the spread of this highly infectious disease, and we used that as a way of modeling, or I guess developing the form for exponential growth. And what we found was this particular equation was good for modeling it: y equals a times b to the exponent x, where y represents the new or resulting amount, a represents the initial or starting value, b represents the rate of growth, so like doubling, tripling, etc., and x represents the amount of time needed for one cycle of growth. So how long does it take to double? How long does it take to triple? That's where you'd be putting that up there. We talked a little bit about what an exponential function looks like visually, and we compared it to Moore's law. And we did a few calculations using that new formula, and now we're going to go on to do a few more. So we're going to go to D here, and it says model exponential growth with equations. So we're going to write a generalized equation from Moore's law. I've already got it written down here for you, but I wanted to sort of zoom in and sort of focus on this part here. Where we have n, which as we know was the number of transistors, 10,000, which is our A value, that's the how many transistors did we have at the start when we developed this law, at the beginning, so 1974. T represents time. Now what's interesting here is I want to point out that I have included here a denominator of 2. And this division by 2, it balances the doubling rate happening every 2 years. So the reason we put this in is how long does it take to happen? In this case, it was 2 years, and that's a number that you can forget. In that, once you start doing calculations, you might forget, oh, it happens every 2 years, not every 1 year. So when you're putting this into your calculator, the way to incorporate the fact that it doesn't take just 1 year to double, it takes 2 years to double, is to include a denominator on your exponent. The thing to remember when we're doing this calculation, however, is that you absolutely must put brackets around this when you're typing it into your calculator, which means that you would type in 10,000 times, let's make that the dot, times 2 to the exponent, or whatever your button is, open a bracket, t divided by 2, close bracket. And I'm talking, obviously, you wouldn't put a t in there, you'd put a number like 1 year, 10 year, 10, 38 years, whatever it is, and then it equals. That bracketing ensures that you're doing the calculation of the time divided by 2 so that you're getting an accurate amount of time going by to match up with the doubling. So let's look at power consumption. So power consumption of computer nodes doubles every 18 months. In 1991, a Cray C90 vector supercomputer required 15 kilowatts of power. So let's use 1991 as our time 0. Let's create an exponential function to model this relation. So I've written this out here again. Every 18 months is 1.5 years. So that's something else I want to point out here, is that we can use months, and that's not a problem, but then we would need to be putting in time in months as well. So obviously, to make the numbers a little more manageable, I would recommend putting 18 months as 1.5 years. So here we go. So n would be the amount of power required. 500 is the initial amount of power required when we developed, so 500 kilowatts. 2 is the doubling, which was mentioned in the question. There it is, doubles every 18 months. And the 1.5 represents the how long does it happen, or sorry, how long does it take to happen. And then t is the time has passed, that is measured in years. So we've developed this equation, now we're going to use it. So we're going to use the equation to figure how much power a supercomputer should use today. So this one we don't have a reference for, so what we can do is we can actually calculate from 1991 and see what we get. So let's start to build this thing. So we have here, so t will be equal to 2020 is what we're in now, minus 1991. And that's going to equal, bang it out through the calculator, so 2020 minus 1991 is going to give us 29 years. So we have 29 years, and now we can substitute this into our equation, since that was the only value we were missing. So here we have n equals 500 times 2 to the exponent. And like I said, this is so important. You want to make sure that your numerator gets calculated before, that your numerator in your exponent gets divided by your denominator before it becomes the actual exponent raised to 2. Oh, I'm sorry, that should be 29. That's my fault. That's a highlighter. That's not helpful. There we go. So that should be 29 rather over 1.5. So I don't recommend doing that calculation. I think you just bang this whole thing through your calculator and see what you get. So what I'm typing in, as I said, is 500 times 2 to the exponent, again, on your calculator. I guess I'll mention it. This little to the exponent bit, it might be, if you don't remember, it might be something like x to the exponent y. It might be something like y to the exponent x. And it might just be like a little hat or something like that. So whatever that button is, do it, and then make sure that you open that bracket. And opening a bracket on my calculator, 29 divided by 1.5, close the bracket, equals, and that's going to give me, alright, sorry, I'm just trying to find the decimal place here. So 330, 280, 743.7. I think I got it all right there. Yep, that looks good. Okay, so that is going to be 330,280,743.1. So that is kilowatts, as I recall. If we wanted to transition this to something other than kilowatts, I don't know how many of you remember this, but the scale from kilowatts to the next 1,000 up from that is megawatts, followed by gigawatts, followed by terawatts, etc. And these are all going up by 1,000. So a megawatt is 1,000 times more than a kilowatt. A gigawatt is 1,000 times more than a megawatt, and a terawatt is 1,000 times bigger than a gigawatt. So each of these goes up by 1,000 each time. So if we wanted to make this number just a little more manageable, we could move our decimal place. So if I wanted to move it, let me just change up my colors here. So if I wanted to move it 1, 2, 3 spots, now we're dealing with a megawatt. And if I wanted to move it 1, 2, 3 spots, that's now going to be a gigawatt. And 3 more will leave me with 0.33, etc. So let's leave it here. So this would actually be, if we wanted just to write it in a slightly different way, 330.28 gigawatts. Now the last part here, according to this model, how much power is necessary in 5 years, we're just going to skip over that question. What you would do is you would add 5 years to 29 and do this calculation again. So is it good practice? Absolutely. But I don't want to eat any more of your time. It's already been a long lesson. So I will say that this homework is really more about knowing how to build this equation right here. Y equals a times b to the exponent x. The homework really focuses on this. The lesson didn't as much, and like I said in the first part of this lesson, it was really because this is designed to be a more of a discussion-driven and relevance-driven lesson that ties into exponential functions of growth. So I would say if you understand how to build exponential equations for growth, by putting in A and putting in B and then substituting in a time and making the calculations, that will set you up well for the homework. The homework is listed at the bottom. It is in your notes. So off you go. Good luck. If you have any questions, again, this is a new concept for everybody, no matter which grade 10 course you came from. So new concept. I totally anticipate you guys having lots of questions. Fire them off. If you're stuck on some of the homework questions, let me know. I'm happy to throw together some more videos. So good luck with the homework, and we'll see you in lesson number 2.